new generation of AI models doesn't just generate an answer, it generates a chain of thought first, working through the problem before committing to a response. The benchmarks improved dramatically. Headlines declared that AI had learned to reason, but what actually happens during that thinking? And does it change the fundamental limits of how these systems work, or just paper over them? Start with what a standard language model does. You send it a question. It predicts the next token, then the next, then the next, each choice influenced by everything that came before. One forward pass, no revision. If the model makes a wrong turn early, it continues down that path, fluently, confidently, incorrectly. This is fine for many tasks. Summarizing a document, translating a sentence, drafting an email, these don't require long chains of sequential correct steps. A single forward pass usually gets close enough. But consider what it means to solve a multi-step math problem. Step 3 depends on step 2 being correct, which depends on step 1 being correct. A human working through this kind of problem checks each step before proceeding. They notice when something feels wrong and go back. They can hold a partial result in working memory, test it, and revise. A standard language model does none of this. It generates, it doesn't verify, it cannot go back. The token that starts a wrong turn becomes the context that makes the next wrong token more likely. The error propagates and compounds fluently until the model produces a confident wrong answer. Try to ask a model to solve a competition math problem, work through a formal proof, or debug a subtle concurrency issue in code. Now the structure of the task matters entirely. A standard model fails not because it doesn't know the relevant concepts, but because it cannot catch and correct its own mistakes midstream. Researchers identified this problem and published a surprisingly simple partial fix in 2022. Simply prompting a model to work through a problem step by step, let's think through this carefully, significantly improved its performance on multi-step reasoning tasks. The model wasn't smarter, it was using more of its inference paths productively. OpenAI's o1, released in late 2024, took this further. Instead of prompting for chain of thought, the model was trained to generate reasoning tokens automatically, an internal scratchpad that works through the problem before producing the final answer. Crucially, this reasoning happens at inference time, not during training. The model spends more compute thinking, rather than generating output immediately. The concrete improvements are real and large. On AIME, the American Invitational Mathematics Examination, a competition that filters the top fraction of high school math students, standard GSP T4 class models solved a small fraction of problems. O1 solved the majority. Similar gains appeared on competitive programming and multi-step scientific reasoning tasks. The mechanism is worth understanding precisely. The scratchpad lets the model backtrack. If a reasoning step produces a contradiction, the model can notice this within the chain and try a different approach, something a standard model cannot do. The reasoning trace is not window dressing. It changes what the model is actually able to compute. Here's the precise limit. Reasoning models can verify the logic of their own steps. They cannot verify whether their premises are true. The scratchpad helps when the task is, given these facts, derive this conclusion. It doesn't help when the facts themselves are wrong, incomplete, or made up by the model. Hallucination, the generation of confident, fluent, incorrect information, happens at the premise level. The model invents a wrong starting fact. Sophisticated reasoning then builds on that wrong foundation. The conclusion is logically consistent with the premises and completely wrong. In practice, reasoning models still fabricate citations. They still confabulate biographical details. They still assert plausible-sounding facts that don't correspond to reality. The thinking is more careful. The inventory of what the model knows is unchanged. There's a second failure mode that researchers have documented: overthinking. A reasoning model will sometimes arrive at the correct answer early in its chain of thought, then, within the extended scratchpad, second-guess itself, explore alternative interpretations, and talk itself into a wrong final answer. On straightforward problems where the initial instinct is correct, a faster standard model would simply answer correctly. The reasoning model overthinks its way to an error. The third reality is cost. Reasoning tokens are not free. Every token of internal monologue consumes inference compute, and therefore money and time. The O3 model at high reasoning settings costs substantially more per query than standard models. This isn't an argument against using reasoning models, it's an argument for using them selectively. Hard logical derivation, difficult code debugging, multi-step mathematics, yes. Summarizing a paragraph or answering a factual question, no. What reasoning models have unexpectedly provided is a form of transparency. When a model works through a problem visibly and gets it right, you can follow the steps. When it gets it wrong, you can often read exactly where the reasoning derailed, not in the final answer, but in the chain that produced it. This matters for practical use. If a reasoning model produces a wrong answer, inspecting the scratchpad often reveals whether the error was logical, a step that didn't follow from the previous one, or factual, a wrong premise stated confidently at the start. Those are different kinds of errors, and they warrant different responses. A logical error might be fixed by asking the model to reconsider. A factual error requires checking the underlying claim against a real source. This transparency is still limited. The scratchpad is generated by the same mechanism as the final answer, and models can produce coherent-looking but wrong reasoning chains just as fluently as they produce wrong answers. Following the reasoning doesn't guarantee you'll catch every error, but it gives you more to work with than a single opaque output. Reasoning models represent a genuine architectural advance. The problem they solve is real, tasks that require sequential, multi-step correctness, where an early error compounds. The improvement on hard mathematics and code is not modest. It's substantial enough to change what these systems can actually be used for. But the framing of thinking carries implications the technology doesn't yet meet. The model is generating more tokens before answering. Those tokens are useful. They let the system backtrack, check logical consistency, and refine. They don't give the model access to facts it wasn't trained on. They don't stop it from hallucinating confident wrong premises. They don't prevent it from talking itself out of a correct answer. The right mental model, a careful analyst who works through problems methodically and catches many of their own logical errors, but who is still working from whatever knowledge they had going in, who can still be confidently wrong about facts, and who occasionally overthinks a simple question into a complicated wrong answer. For the tasks where methodical, step-by-step analysis matters, these models are meaningfully better tools than what came before. For everything else, a faster and cheaper standard model will often serve just as well. Understanding exactly where a tool's boundaries are is what separates using it well from using it blindly. If that kind of precise look at how AI actually works is useful to you, subscribing is how you get more of it.